Okay. What I'm going to talk about today is on sampling, and it's also stuff that you're going to be doing in lab in a couple weeks when we do our Naproxen sodium lab. So I'm going to go back, talk a little bit more about, well, I'll talk about physical properties and the chemical properties of chirality and how that affects those. So the first issue is, what's different about enantiomers? And so if you have two enantiomers, and now we've talked about one and multiple chiral centers, the enantiomers are a pair of mirror image isomers. Okay, it doesn't matter how many chiral centers they have, it's a pair of mirror images. So if they have one chiral center, one's R, one's S. If there's two chiral centers, then if they're RR, the other enantiomer's SS. Okay, so we have those pair of enantiomers. They're mirror images. So what's different about them? Physically, the only difference between enantiomers is how they rotate plane polarized light. Okay, so that's the first thing we have to talk about. And then the question is, well, what is plane polarized light? Well, plane polarized light is the light that you get when you pass any light through a polarizing filter. So if you have polarizing sunglasses, the light that's coming into your eyes is light that's oriented in one direction. So if we looked at, if we looked at electromagnetic radiation, there's actually two components to electromagnetic radiation. There's an X, Y, and Z component. So if I looked at the three-dimensional view of a wave of light, there's two components. There's an electric vector and there's a magnetic vector. And they're perpendicular to each other. So that sine wave of light is actually two components, an electric and a magnetic vector. And you'll talk about that in physics if you haven't taken it or if you are taking it. So what a plane polarized filter does is it blocks the orientations of light so that only one orientation passes. So if we had, for instance, if we looked at light, we would have all these different orientations of light, all 360 degrees of orientations of these magnetic and electric vectors coming at us. So that's what we're seeing now. If I put up a polarizing filter, it basically blocks it and only one orientation is allowed through it. And it depends on how I hold the filter. If I rotate the filter around, then I can get different orientations of the light. So it's kind of, the other model that's used is, it's kind of like a picket fence. All right, there's my example of a picket fence. So only the light of one orientation passes through the pickets, or the vertical stakes. So when I come up with when I use plane polarized light, I use a polarizing filter, the light passes through it, I then can pass it through my sample. And what happens is that if the molecule is chiral, meaning that it is existing in one of two handed forms, one of two enantiomers, and there is an unequal mixture of those two forms, could be 100% of one, could be 51-49, but if they're unequal, the enantiomer rotates that plane polarized light by some number of degrees, which we call alpha. Okay. And so the light comes through and it gets rotated by some number of degrees. And that degree of rotation can either be positive or it could be negative. So in other words, it could be clockwise or it could be counterclockwise. And so the story of this goes, and I think it's more myth maybe than reality, but it makes a good story, is there was Louis Pasteur, right, the guy that invented milk. Like when my first teaching job was at Kansas State, and I made that joke, and when I left, there was a whole smoking congregation outside the door, and they made sure, he really didn't invent milk, and I said, I know it was a joke. But they had a hard time telling whether it was a joke or not. But Pasteur did lots of things. And one of the things he did with chirality is that he was in France. They grow wine, make wine. And so I guess in the bottles, really old bottles, you'll get these crystals form on the corks. And if you look at them under the microscope, there's actually, I guess, 3 forms. There's 2 that are mirror images of each other, and then there's a third one that has sort of a mirror plane of symmetry, so it isn't chiral. So you can pass a mirror plane of symmetry through it, and it's the same on both sides. It's kind of like this. This has a mirror plane of symmetry, right? I can cut this in half. But my hand, I can't, right? There's a left and a right hand form. So what he did was, the story is painstakingly with tweezers, he separated these out into like 3 piles. And then he knew about using plane polarized light because somebody else had invented that. And so he then passed the plane polarized light through solutions. And what he found was that one of the mirror image crystals rotated to the right, the other mirror image rotated to the left, and then there was the one that didn't have a mirror plane, and it didn't rotate at all. And then he started mixing things together, so he mixed equal amounts of the left and the right-handed crystals and got them to cancel out. So this is the only physical property that's different for enantiomers. If I think I have a chiral molecule, the only way I can tell, well, initially the only way to tell is use a polarimeter and pass plane polarized light through it. Okay? So that's what we do. And it turns out that number of degrees of rotation is going to depend on these 4 things. The exact compound you're using, because each chiral molecule rotates a different number of degrees. It depends on the length of the sample cell. So in other words, how long is the cell that the light's passing through? What's the concentration of the sample? And then the solvent. And solvent doesn't really play a big role in this. So the 2 we're going to focus on, how does the length of the cell and how does the concentration affect that number of degrees? And so it's actually proportional. The length of the cell, the longer the cell, the more molecules the light interacts with, and the greater the rotation. So if you double the cell length, you double the number of degrees of rotation that you see. It's a direct proportion. If you double the concentration, there's twice as many molecules interacting with the light, and so you double the rotation as well. So the cell length and the concentration are proportional to that number of degrees alpha, whether it's positive or negative. Okay. Now, why is that important? Well, in a couple of weeks in lab, we're going to look at a chiral drug called Naproxen sodium. Right? Naproxen sodium is Aleve. Right? So there's also an ibuprofen that's chiral. I don't know if that's widely available on the market. But the idea is chiral drugs will cure your headache faster than a mixture of the 2 enantiomers. Okay, so they say like ibuprofen chiral ibuprofen will cure your headache in 20 minutes versus like an hour for the mixture of the two. Well, let's say that I work for the drug company that's making ibuprofen or Aleve, and I have this solid, and I have to make sure that it's one enantiomer and not the other. Because when we talk about Aleve tablets, basically one enantiomer cures my headache, the other one does damage to my liver. So if I want to keep my job at the drug company and not have the drug company be taken over or go bankrupt because of lawsuits, I need to make sure that it has the right enantiomer that's being sent out. Right? And, a little liver damage is, well, it's worth a lot of money when people start suing. The worst case of that that's ever happened is a drug called thalidomide. And in the 60s, it was used as a sedative. And there are two enantiomers of thalidomide. One was a sedative, one caused birth defects. Really horrible birth defects. So don't Google it unless it's very bad stuff. They didn't find that out until they started having these thalidomide babies, and then they stopped the drug. I don't quite understand how it's, because I have that chart of generic drugs outside the organic lab. I think it's like number 10 back in 2008 of the top 10 generic, or of the top 100 generic drugs. If I was a drug company, I wouldn't touch it, right? Because you could just hear the ads on TV. It would be like, pregnant women shouldn't be in the same county as this drug, let alone anything else. So it somehow they're selling it as it's pure enantiomeric form. So enantiomers, and we'll talk about this, but enantiomers can do different things chemically, so they have different chemical properties. But in terms of physical properties, the only way I can tell whether I have the right-handed or the left-handed form is to use polarimetry. So I need to know, well, what number of degrees am I looking at? First, I need to know whether it's positive or negative so that I've got the one that cures my headache as opposed to destroying my liver. And then I need to know how many degrees it is because I want to make sure it's 99 point, probably 4 or 5 nines after that pure. So I need to know that exact number of degrees. Well, what happens if I'm doing that and somebody else at a company, because probably they have a branch in Europe, we have to make sure that we get the same number, right? So we have to either make sure we're using the same concentration, the same cell length. Any of those changes, we're not going to get the same number. So what happens is that we end up standardizing or normalizing that number of degrees of rotation that we get from the instrument. We calculate then what's called a specific rotation. So the specific rotation is our alpha in brackets. And that is calculated by taking the experimental rotation, which was the number of degrees that we determined from the instrument. We have the cell length, which is in decimeters. And historically, organic chemists don't like math, apparently. So all the cells are 1 decimeter in length. To make the math easier, that's 10 centimeters. Ours is 1.1 decimeters, because it isn't quite 1. And then the concentration. Well, a lot of times, I may not know what I have. So I can't use a molecular weight if I don't know what the identity of the compound is. So this is normally measured in grams per milliliter, because I can make that solution up all day. I don't need to know what it is. I just weigh out so many grams per milliliter. So when you use this equation, then what happens is then it normalizes it for the cell length and the concentration, so you get the same specific rotation regardless of the concentration and regardless of the cell length. So everybody's going to report the same specific rotation for that compound regardless of the conditions they use. And normally we specify a solvent, although that doesn't make much of a difference. So this is called the specific rotation. The 20 degrees, normally that's what we're measuring. The instrument is at 20 degrees, and the D turns out to be what's called the D line of sodium. So typically these instruments will use a sodium arc lamp. These used to be the street lights. They had that kind of orange glow to them. And so there's one very specific wavelength that you use for this. So we have these instruments called polarimeters. We have one in the instrument room that we'll be using in a couple weeks, twice, for 2 experiments. And so we can measure the specific rotation. And there's a literature value for every compound then. So for instance, for Naproxen sodium, if I remember correctly, it's minus 11 degrees. So that means that if I worked at the plant and I was making all of this Naproxen sodium, if I measured its specific rotation, it better be minus 11. If it's plus 11, I got the wrong enantiomer. If it's plus 8, that means I have an enantiomer in there that I'm not supposed to have. Okay. So the specific rotation is what we use to measure, and it takes into account the cell length and the concentration. So everybody should get the same value. Okay. So that's the importance of the specific rotation. I like it when this thing just goes absolutely berserk. All right, what did I do? So here is Naproxen sodium. There's over here, it's a CH with a CH3 with a C double bond O, O minus with an Na plus. And that's my chiral center. Okay. Naproxen sodium is a deprotonated carboxylic acid. Right, and in lab you did that last week. You took the acetosalicylic acid and added NaOH to it to deprotonate it and to put it into the aqueous layer so you could separate it. When they sell Naproxen sodium, they sell it as the carboxylate salt, as the deprotonated carboxylic acid. When it gets in your stomach, it then gets protonated and becomes Naproxen. And one of the things we're going to find is that this is like, what did I say, minus 11? I guess I'm way off. Somebody's way off. But actually, when we make Naproxen, because we're going to make both, we're going to simulate what happens when it gets in your stomach. Naproxen's a different compound, so it has a completely different specific rotation, and it's plus 66. So we're going to do both, and we're going to see how pure the compound is. But one of the things we can do is, whenever we're making chiral molecules or analyzing chiral molecules, we have this thing called the enantiomeric excess. Okay. And again, this is important for lab, but it's also Sapling will ask you some questions on this. The enantiomeric excess is simply the percentage of the major minus the percentage of the minor enantiomers. And whenever somebody's making a chiral molecule, they always say, we got this percent enantiomeric excess. For a drug, we would like that to be 100.0. Right? Because usually the other enantiomer does bad things. So we want 100% of the enantiomer that's doing what we want it to do. But if I'm synthesizing it, I may not get that. So let's say I had a mixture that was 75%, 25%. Well, the major enantiomer, if it's plus or minus, is going to then give you the overall sign of the mixture. So that's the first thing we can tell. Whatever the sign of the mixture is, that's the major enantiomer. But what happens? What happens is that the minor enantiomer basically subtracts. We remember what a racemic mixture is? Yes? No? No? Okay. A racemic mixture, just so we're all on the same page, is a 50-50 mixture of enantiomers. That's a racemic mixture. Okay. And that's so a racemic mixture is exactly 50-50, is exactly 1-to-1. And I believe that racemic term comes from going back to Louis Pasteur. That was the crystal that had a mirror plane in it. That when he took it and dissolved it in water, it didn't have any rotation. That was called, I think, racemic acid for some reason. So a racemic mixture is a 50-50 mixture. Well, a 50-50 mixture would have an enantiomeric excess of 0. 50 minus 50. Well, enantiomers rotate the plane polarized light in two different directions. The one that rotates in the positive direction, so in other words, the one that rotates the plane polarized light clockwise, is called the D enantiomer for dextro. The enantiomer that rotates counterclockwise is called the L enantiomer for levo. So when we have a pair of enantiomers, we've got the D and we have the L. So we've got the dextro, we've got the levo. And it turns out their specific rotations are exactly the same numerically, but just with different signs. So 50-50 mixture then, they're going to cancel each other out and you're going to see no rotation. You're going to see 0 degree specific rotation. Everybody kind of with me? So we have left and right-handed forms. Those are the enantiomers. One rotates positive, the D. One rotates negative, the L. If they're 50-50, you get no rotation. If they're unequal, you get a rotation of the major product. But then what does the other product do? The one that's minor basically subtracts from the major. So if I had 75% major, 25% minor, the 25% minor subtracts 25% of the major, cancels it out. That gives me 50% of what I would expect for 100% of the enantiomer. So let's say I had naproxen sodium. If I have, using my numbers on this chart, if looking on this slide, let's take the 17 because it's easy. If I have 100% L naproxen sodium, I would get a specific rotation of minus 17 degrees. Okay. L meaning it's the levo, it's got the negative sign. If I had 100% D, it would have a specific rotation of plus 17. If I had a 75-25 mixture, that means the resulting solution would have 50% of the original 100%. So if it was 50% of the negative, that means I get 50% of 17, which is what, 8.5. So if I had an 8.5 degree rotation on my Aleve that I just made at the factory, I would take that 8.5, I divide it by 17, I get 50%, and I'd say, oh, it's a 75-25 mixture because those are the two numbers that add up to 100, but when they subtract, make 50. So then I'd say, well, I can't sell that because it's got 25% of the liver damaging enantiomer in it. So the enantiomeric excess is what we use to determine the purity. And sometimes I call this the optical purity of an enantiomer. So if I'm trying to make it 100%, I want an enantiomeric excess of something in the neighborhood of 99%. Because 99% would be 100, it'd be 100 to 1. I don't know how that works. It'd actually be 99.5 to 0.5 would be 99%. And I'll show you actually we don't use the rotations to get that level of detail because there's no drug company that uses rotations that's still in business. Because I need to know to like 3 decimal points how pure it is. Okay. So that's what the enantiomeric excess does. So it's fairly simple to calculate. Just you take the major minus the minor. So then there's 2 ways to do this, and this is in your lab book. If we had a specific rotation of minus 12 degrees, and I don't know why I'm determining that it's minus 16 because now I'm confusing myself because I thought it was minus 11 to begin with, and now it's minus 17. If I had something that was minus 12 and its specific rotation of the pure negative naproxen is minus 17, here's what I would do. I would take the 12 over the 17 times 100, and that gives me the percent enantiomeric excess. That's what it would tell me. And if I did that, what would I get? I get 70, well, let's just round up. I get 71% enantiomeric excess. And then I need 2 numbers that add up to 100, but when subtracted, give me 71. So if it's me, I do this by trial and error. I go what? 90-10 is 80. 85-15 is 70. Close enough. So this is like an 85-15 mixture of the 2 enantiomers. Actually, it would be what? 85.5 and 14.5, if I want to get it exact. If you don't like that, there's a method in your lab book where they take 2 equations and 2 unknowns and they solve for X and Y. But I just do it in my head. Right. So, and it will ask you in sapling to calculate enantiomeric excesses, and that's how you do it. Just take the resulting, and because the mixtures is negative, that means it's an 85-15 mixture of L to D, because the L is the negative, by definition. So the whole point of using plain polarized light is that it's the only way I can determine whether I have the D or the L enantiomer, whether I have an unequal mixture of enantiomers, and whether I even have a chiral molecule at all. Because if a molecule has no chiral centers, it's going to have no rotation. If, on the other hand, it's a 50-50 mixture, it's going to have no rotation either. It's going to have a net zero. Okay. But if I have an unequal mixture, I could calculate the percentages if I wanted to. We're going to do 2 experiments in lab with rotations where we're going to measure those. The second one is we're going to take a compound, we're going to use yeast to reduce it from a carbonyl to an alcohol. And when we do that, we make a chiral center, and we're going to try and determine what the percentage of the enantiomers are from that yeast reduction. And it turns out the enzymes in yeast will reduce to one of 2 enantiomeric forms. So, that's enantiomers. Enantiomers have different chemical properties, but only when they react with another chiral molecule. My analogy for that is, in the lab, we don't have 2 boxes of gloves, right? We don't have a box of left-handed gloves and right-handed gloves. We have uno box of gloves, and that's because there's a mirror plane that goes through the gloves. So even though my hand is chiral, when it reacts with a chiral glove, there's no reaction, right? There's no, I have to put on another glove. On the other hand, if I have any other kind of glove, winter's coming, winter gloves, golf gloves, whatever gloves you've got, if they don't have a mirror plane, they are chiral. Well, left hand into right-handed glove is a different reaction than left-handed into left-handed glove. Right? That's true for drugs too, or chiral molecules. If you have one enantiomer and it reacts with another, with only one enantiomer of another molecule, it will react differently with those 2 enantiomers. And that's the problem with thalidomide. Thalidomide, those 2 enantiomers react with another chiral drug, one sedative properties, the other birth defects. And most of the molecules in our body, or at least the good ones, the ones that are important, are chiral. And not only are they chiral, they're just one form. Amino acids, all one form. Sugars, all one form. Matter of fact, we can't metabolize the other enantiomer of sugar. Right? There's this classic essay question that sometimes people ask. They'll say, Alice apparently went through the looking glass and became the mirror image on the other side, and she couldn't find anything to eat because she couldn't metabolize anything, the other forms of the sugars. So then they ask, well, what biomolecules could she actually eat, et cetera. But I don't ask that question. It's kind of an interesting idea. Drugs, we have to be careful because if we have one enantiomer of the drug and the other one, how does it react? Does it cause liver damage? Does it cause birth defects? The FDA went through a phase, and they still may be in it, where if you made 100% of this one, you had to show that this one actually didn't have any benefits, which I didn't quite get. I could see making sure it wasn't harmful, but benefits, I think this one is the important one. And since most of these go into your stomach, what happens when they react with acid? Because it does you no good to make thalidomide in one form. It gets in your stomach and makes both forms. Right? So you can't have chiral centers being affected by acid if they're going to go through your stomach and probably your blood. So chiral drugs are, and there's lots of them. I think one of the pre-lab questions is look on the internet and see what kinds of chiral drugs there are. I think the purple pill, that's not on TV as much as it used to be, but Nexium, that's another chiral drug that they make in one enantiomeric form. But all the biomolecules that are important are all one chiral form. So they have the same physical properties, it's just their chemical properties are different when they're reacting with something else chiral. All our enzymes, all our proteins, all our sugars, chiral, one form. So that's why this becomes important. What happens when we have two chiral centers? So this is where it gets a little confusing. Because I have two enantiomeric forms, left, right. How many chiral centers? Doesn't matter. Because every chiral center is opposite in the enantiomer. So if I have 5 chiral centers, all 5 of them are the opposite configuration in the enantiomer. But what happens if I only switch one chiral center? Well, then I get a diastereomer. So here's 2 diastereomers, pseudoephedrine and ephedrine. Both of where you can't get ephedrine anymore, and pseudoephedrine you can only get 3.5 grams a day from the drugstore because otherwise you're making meth with it. That's the assumption of the pseudoephedrine control act of whatever it was. So the only difference between ephedrine and pseudoephedrine is this chiral center, which is opposite. Those 2 chiral centers with the methyl group are the same. So these are diastereomers. Diastereomers turn out to have different physical properties altogether. And if they have different physical properties, they have different chemical properties. So when you have more than one chiral center, if this molecule had like 5 chiral centers, it has one and only one enantiomer. It's got a whole bunch of diastereomers. So, pseudoephedrine and ephedrine, one melts at 58, the other one melts at 37. Pseudoephedrine you would take if you had a stuffed up nose. Ephedrine, probably you would do the same thing, except it's causes your metabolism to increase. There used to be this stuff called fen-phen that was on the market. There was ephedrine that people used to take to speed up their metabolism to lose weight. There's lots of other illegal drugs, and it's now illegal, that speed up your metabolism as well. So those are the 2 drugs. They have different physical properties. They have different chemical properties. So actually, I can separate those. If I go back to enantiomers, same boiling point, same melting point, put them on a TLC plate, same spot, run them through a gas chromatograph, a normal gas chromatograph, 1 peak, same boiling point, same refractive index. Diastereomers, they have different properties. Sometimes they're very similar, but they're different. They're not exactly the same. So I could shoot pseudoephedrine and ephedrine into the GC, and I would see 2 different peaks. Of course, that's done on a routine basis in either a toxicology lab or a crime lab, when they pick up somebody who had a lot of pseudoephedrine because they were doing nefarious things with it. But there's times when I want to separate enantiomers. Think about, I'm working at the drug company, and I'm trying to make 100% naproxen sodium. Well, I need to find a reaction that gives me 100% naproxen sodium. Well, that's a little difficult. Now, if you want to make a chiral molecule, you need to use a chiral molecule as a reagent. We'll find that out when we use the yeast. Because the yeast have chiral molecules, so they're able to make one product over another. Or you make them in 50-50 and you try and separate them out. Well, how do you separate something that has 2 exactly similar properties? Can't do a TLC on them because it's the same spot. So sometimes we do things like this. Let's say I had a carboxylic acid, a chiral carboxylic acid, and I could react it with an alcohol to make an ester. We'll learn that reaction next semester. That's called esterification. Well, if I have 2 alcohols, 50-50, and I react them with a chiral carboxylic acid, I end up making 2 different compounds. Because the chirality of the carboxylic acid part stays the same, while the chirality of the alcohol is different. So when I look at the two molecules, the two esters that I make, one has they have the same configuration here, and opposite configurations there. If at least one chiral center is the same, and at least one chiral center is opposite, you have diastereomers. And if you have diastereomers, guess what you can do? You can separate them because they have different physical properties. So I can take these, I could put them on a TLC plate, I'll get 2 spots. And I can separate them. After this week, you'll know when I say we can put them on a column and we can separate them that way. And then what do I do at the end? If I want my alcohols back, I can use what's called base hydrolysis of an ester, rip the thing apart, and make my 2 alcohols. And so I can separate them that way. That's kind of a pain. This is a classical way of separating chiral alcohols. It's called a Mosher ester. So it's really difficult to analyze and separate enantiomers. It's really easy to analyze and separate diastereomers. But most of the time we're interested in enantiomers. Right, here's an example. So I get involved in a lot of strange research. And one of them is like looking at essential oils using the gas chromatograph mass spectrometer. Right, the thing from CSI that solves all of our problems along with DNA. And it really doesn't, but that's how it is sold. So one of the more popular components that are in essential oils, and you made clove essential oil in lab. Look at that. I mentioned lab numerous times in lecture. We made clove essential oil. We didn't look at all the individual components of it. We just looked at 2. But there's tons in there. So one of them, which I don't believe is in clove oil, or not very much of it is, linalool. Linalool has a chiral center in it. And it turns out that linalool has 2 different enantiomers. One gives a flowery, fresh, lavender-like smell, because lavender has linalool in it. The other enantiomer is herbaceous, musty green, having a citric note. Problem with essential oils, perfumes, colognes is their smells, and the only way to describe a smell is by using big words. You can't patent a smell. You could patent a composition, but you can't patent a smell. You can't copyright a smell. You can copyright music because there's actual notes that go with it. A paper form, there's no paper form of a smell. So those 2 enantiomers have different smells, which means that inside my nose, or somewhere along the line, there must be chiral molecules to make that differentiation. And there's a whole neuroscience behind this that I know nothing about, but that's smell. And then taste is like mostly smell. So you have this linalool could have 2 different smells. So I think this is an instrumental analysis project they kind of do, at least the first part of it. So first is, well, where's linalool found and what kinds of essential oils? Right? Essential oils have all these individual building blocks in them, all these individual components. And what you do is you essentially mix essential oils together to make your perfumes and your colognes. And you can also use those to flavor soft drinks. Okay. So what we find is that there's 4 oils that have a high percentage of linalool: coriander, rosewood, hoe wood, and hoe leaf. The hoe leaf and wood are from China. The hoe leaf would be better than the wood because then you could just strip the leaves off and the tree would regrow them, whereas the wood, you got to cut down the tree. And that's the problem with rosewood, is that's actually an endangered species, right? So they don't use rosewood very much anymore for guitar frets and other things because it's endangered. So those are the 4 essential oils that you get. And then there's a whole bunch of other ones, lavandin, lavenders. One of the students, we started a project looking at this with lavender and lavandin and spike lavender. I know way too much about this stuff, but this is where you can find all these linoleuls. Well, what we wanted to do is we wanted to say, okay, are the enantiomers different in these different essential oils? And you could use that to authenticate them, but they're going to change their smells. Right? If you have one that smells more like lavender and the other one that smells musty green or whatever it is, right? Start mixing those together and you're going to get a different smell than if they're pure. Well, how do you determine the percentages? Well, you could use specific rotation, but it's not very sensitive. And a drug company would never use specific rotation to say my product is 100% minus and 0% of birth defect causing drug. So what we do is we take advantage of this diastereomer effect, that the diastereomers have different physical properties. And what we do is we take a GC column and we put a chiral molecule on the inside. One enantiomer of a chiral molecule. It's called cyclodextrin. And what happens is that if we make our column with just the D form of the cyclodextrin, as the linalool molecules go across, they end up interacting with the stationary phase. And then, of course, when they go into the gas phase, they move. This was originally done with TLC plates. They coated the TLC plate with a chiral molecule. It was what's called a Perkel column. I don't know if he won the Nobel Prize, but he's very famous for that. What happens is as your enantiomers of linalool move across the column, they interact differently because here we have plus plus and here we have minus plus. That's a set of diastereomers. And so when you have a chiral column, when you have a chiral molecule in your stationary phase, all of a sudden one peak becomes 2. And so now you can separate them. You can integrate the peaks. And so at a drug company, if they want to know they've got 100% of one drug, they use a chiral column of some sort. And how well does it work? It works great. So if I take my linalool and I buy the racemic version that somebody synthesized in the lab, which will become important in a moment, or I take, somehow they separated out, and they didn't do a very good job, but they separated out into one of the 2 enantiomers. If I put those through the GC with a chiral column, now you can see I get 2 peaks for the racemic. And the one that's minus, there's a little bit of plus. There's a little bit of plus in there. But I can integrate that and I can tell you exactly how much plus is there. Right? If this is going to cause birth defects, we can't have any. But this instrument is sensitive enough to detect that. So now we can actually determine our percentages of R and S. Okay, I'm using essential oils. It's not going to kill anybody. But it will change the smell. And it might change for a perfume manufacturer. They might say, well, I want this one and not that one. So then we looked at the 4 big ones, the whole leaf, the whole wood, the rosewood, and the coriander oils. And what we actually see is that the whole leaf is 100%. That company just should have used whole leaf because there's no R in there, or there's no plus in there at all. Rosewood, it turns out, if you look at enough rosewood samples, they're always an uneven mixture, but they kind of go both ways. But it's never 50-50. Because if it's 50-50, that means somebody synthesized the linalool, which you can't get synthetic linalool in a natural essential oil, so that means somebody adulterated it. And the coriander turns out to be mostly plus in all the samples. And so then you just run a whole bunch of You just go on the internet and you just buy like every Rosewood you can find. And we found all the hoe leaves are like almost 100%. When we go to Rosewoods, there are some Rosewoods that people were selling that aren't Rosewood, like this one. But hopefully nobody knows anybody who owns this company. There is a company on here who the current research student's mother owns that company. She goes, "Oh, that's my mother's company." And I go, "Oh no, hopefully she's selling the good stuff." But this is most likely hoe wood. Anything in here that's like 50-50 like this, I'd have to wonder if that's not synthetic. Now, again, this is just, and I don't blame any of these companies. I've never written them saying, "Hey, you're selling the wrong stuff," because my legal team advises against that. But if you think about something where the stakes are higher, like a drug, that's going to potentially kill or maim somebody, you need these kinds of techniques to be able to do that. But it's basic enantiomers and diastereomers. Okay? All right, so that's our little talk about, my little talk about optical rotation. You will need that for sapling, and we will encounter it in a couple of weeks in lab. Okay? All right, Wednesday we're going to do some more problems, so if you have any questions about any of the problems you've done so far, bring them on Wednesday and we will talk about them as well as do more.